Welcome back to our AP Chemistry notes over buffers. It's the section of Chapter 11 that we are now discussing. A bit of review. I wanted to point out again that we have the shortcut to using a Rice table and a Ka expression called the Henderson-Hasselbalch equation. And if you know you have a buffer situation, it works really well because all you need is 3 of these 4 variables. And you can determine the other, one that's left out. So it's a great handy way to do one calculation and get the same work as a Rice table and a Ka expression and solving for x would give you. On the other hand, if you're more comfortable with a Rice table and a Ka and solving for a x, then please go that route, because what you're more comfortable with is probably the one you will least likely mess up come the test, because you are going to be under quite a bit of psychological strain that day and you want to be doing what you're comfortable with. So what we are going to look at is what effect a buffer actually makes when we do something like add some base to an acid. So we have buffer systems in our bodies or anywhere else that we have buffers. It's there to minimize the change that adding additional acid or base causes to the pH. So some examples for you. If I have 1 liter of pure water and I add 0.10 moles of sodium hydroxide to that, the pH would go, and this is at 25 degrees, would go from a pH of 7 to 12. So that's a difference of 5, okay? Which, as we know, the pH scale is based on a logarithm scale, so that is actually something like, if I'm moving the decimal enough time, that's 100,000 times more basic there. Now, what if instead of water, I start with acetic acid, a 0.1 molar solution, which does not sound very concentrated. But if I start with a 0.1 molar solution of acetic acid, that starts at a pH of 2.89. If I add that amount of sodium hydroxide to it, I end up with a pH of 3.78. So starting with an acid means adding that base to it changes the pH already by only, that's like less than 1 pH level. So that's a less than 10 times change there. But what if I had a 1 liter acetic acid and sodium acetate buffer? How much would it change then? So again, I point out what we're trying to contrast. Pure water changed to pH of about 5. 1 molar acetic acid would change the pH a little less than 1. Let's just kind of round that to 1 for the sake of our discussion. So a change of 5, a change of 1. What's going to happen if I had a buffer? Now, in order to know what's going to happen, I have to know what we're going to start with. So that's our initial step. We're going to find the original pH of just the buffer itself. Because remember, making a buffer by adding a salt to your acid solution is going to change the pH. 2 ways I could do this. I could do this with the Henderson-Hasselbalch equation. I could do this with the Rice table and Ka. I'm going to do it with the Rice table and Ka, because I'd rather you know this way, which works for everything, than the Henderson-Hasselbalch, which only works for buffers. But again, if you can identify that it is in fact a buffer system, you can take that shortcut. Anyway, so I have acetic acid, which is HC2H3O2. And I'm going to add it to water, and I'm not going to write in the water. And it's going to give me hydrogen ion, and it's going to give me acetate ion. Now here's the thing, as I start my Rice table, initially I think I have a 0.100 molar solution of that, but check out what else I have. Because I have 0.100 molar solution of sodium acetate, well, sodium acetate is very, very soluble and is going to ionize completely, one-way arrow. And it's going to ionize, give me sodium ions, which I don't care about, and the acetate ions, which I do care about. That's a 2, I guess. There you go. Okay. So 0.100 molarity of sodium acetate, one-way arrow, so 1-to-1 ratio, 0.100 molarity. So I'm also starting with 0.100 molarity of that. Okay. And I'm going to change and use up some of that. I don't know how much, and I'm going to add some of that. And I had, if you want a 0 there to fill in your Rice table, that's just fine. You can leave it blank. No one's going to care. All right. And as this is a weak acid, and because the Ka is 1.8 times 10 to the minus 5. Now, how do I know that? Because I've used it so much I've memorized it. How would you know it? It would be given to you, or like in your classwork, you go to your charts, your appendix, and you find the Ka of acetic acid, and there you go. So given that information, I am certainly going to make the assumption okay. So Ka is, and I would write a statement about assume, okay, and we've been there a lot, so I'm not going to show it on the screen. But I most definitely would be on the AP test. I'd be like, assume the concentration because the Ka is so much smaller than 0.1. And that is an H plus there, by the way. I'm not sure why the pen is not writing well. Concentration of C2H3O2. Okay, so there's my Ka. Plugging in what I know 0.100 molarity times X divided by 0.100 molarity equals 1.8 times 10 to the minus 5. Hard. Okay. Well, hey, this is really handy. Check this out. We know those reduce to 1, so I have what X is. But X does not answer my question. X is the concentration of hydrogen ion. But that even does not answer my question. I'm needing pH. So to finish it up, pH equals the negative log of the concentration of H+, which equals the negative log of that. Okay, and I can already tell, since my exponent there is negative 5, that the pH is going to be below 5. If it was a 1 times 10 to the minus 5, it'd be exactly 5, but since it's 1.8 times 10 to the minus 5, it is going to be less than 5. So I'm going to take the negative log of, well, what help the calculator would do what I ask it to do. Negative log of that, 4.74. Okay, let's discuss this. What is this? This is the starting pH. Okay, starting pH of the buffer. So, wow. So previously we talked about how acetic acid on its own starts at 2.89. Well, as this buffer of equal amounts of acid and salt, it's now going to start at 4.74. Now that alone makes a huge difference, but we've already discussed how the Chateliers kind of predicts that for us. We expect the ionization to decrease as we start with some of this common ion effect. And if that decreases, we get less H+, which means the pH will be closer to 7, closer to neutral. Anyway, we're going to come back to this number in a few minutes, but that's our starting point. Now, how do we continue? So now that we know what the original starting amount of our buffer is, we're going to figure out how does that change when we add sodium hydroxide. So before I start any of my new work, I'm going to do my neutralization reaction. I'm going to pretend that happens before the buffer sets up. Obviously, it's happening after, but chemically speaking, it works out the same. It's just easier to do it in this order. So I'm going to start with my reaction between, let me pick a color to make it different. I'm going to start with the reaction between sodium hydroxide and acetic acid. So I have an acid and a base, and it's going to be a double replacement reaction and give me water and sodium acetate ion, or sorry, sodium acetate salt. Okay, now check this out. I'm going to draw this as a one-way arrow because sodium hydroxide is a strong base. By definition, a strong base is not going to associate. It's going to fall apart. It's going to dissociate. So I would never, by definition, I would never have a reverse reaction occur. So it's going to force this to completion. Now I'm also mixing some solid sodium hydroxide to a liquid. So I'm not going to change the volume of the liquid in total, but when you do add a liquid to a liquid, you get that dilution, and you do want to be careful you account for that. So what I'm going to do is I'm going to still do it the way I would and work in moles. So I'm going to build a little quick neutralization rise table in moles. I have 0.010 moles of sodium hydroxide, and 0.1 molarity in 1 liter, I have 0.100 moles of acetic acid. And we're going to pretend I have no moles of water. And check this out. Okay, we do have some sodium acetate already. Okay, how much sodium acetate? We have it right there. 0.100 moles of that as well. Now I have over here a limiting reactant situation set up. So which one is going to be the limiting reactant? I hope you say it's very obviously going to be the sodium hydroxide. So I'm going to subtract that from both sides. If I subtract it here, I'm going to add it here. And you know what? We don't really care about the water. So let's add it here. And now I total it all up. Sodium hydroxide actually zeroes out, which is good because it was the limiting reactant, and it's a one-way arrow. And my acetic acid, I have this left. That's moles though. And for my sodium acetate, I now have this new combined total, and that's moles. Okay, well, for what I'm about to do, I want molarity, and this is where I can account for the dilution. So I'm going to divide by the entire new total of solution, which is still 1 liter, because I added solid sodium hydroxide, not liquid. So this is now molarity, that's now molarity, I'm good to go. My next reaction is the normal one of acetic acid, C2H3O2, that is a 2, forming hydrogen ion and acetate ion. And my starting amounts are different this time. Check this out. I'm starting with 0.090 molarity there. And I'm starting with 0.110 molarity there because, again, sodium acetate will ionize, one-way arrow, will ionize completely into sodium and acetate. And it's a 1:1:1 ratio. Now be careful, because the moment you don't check that there's a ratio there and you take for granted it's a 1:1 ratio is the moment it won't be. So be careful. Now I don't know, I'm not starting with any hydrogen ion, or at least I'm pretending I'm not. And we're going to subtract X there. We will add X there, we will add X there. And I would check to see if I can make the assumption, and we would say yes. Ka is small enough we can assume. So I would write the assumption statement. I'm not going to, but you would write the assumption statement. So check out what this does for us. I still have just a single X, and Ka, which you know as concentration of products over reactants, is going to be, if I could write enough ones, that times that divided by that. And I looked up Ka, and it's 1.8 times 10 to the minus 5. Nope, don't do that. Okay, so now I need to solve for the X. Okay, and be very careful as you type this into your calculator. 0.110 divided by 0.09 gives you 1.2222. So I'm going to take my 1.8 EE to the negative 5, and I'm going to divide by the answer I had there, that 1.22222. And I see that I have now an X equal to, that's just supposed to be an X, sorry, there's not a prime or anything, that's just regular X. X is equal to 1.47 times 10 to the minus 5. Sure, let's go 2 slides ahead. Why not? And now I'm going to answer my question by actually finding the pH. So X is the concentration of H+. So my pH is, the negative log of concentration of H+. So it's the negative log of that number there. So I'm going to go negative log of the number I just got. And I see my pH is 4.83. Okay, so There's my pH after the sodium hydroxide has been added. Does that kind of seem like deja vu? Well, go up. You have the ability to go up a previous slide. Previously, what was our pH? About 4.7. Now what is it now? About 4.8. So adding sodium hydroxide, a base, to an acetic acid buffer solution meant the sodium hydroxide changed the pH about 0.1. Actually a little less than even 0.1 of a pH. Remember, without the buffer, it changed it about 1. And without any acid in it, it changed it 5. So the effect of a buffer is really profound. Does this mean, well, why can't we make all of our things buffers and then be sure it's at the same pH like forever with very little change? Well, you can absolutely eventually overload your buffer. What if I put in enough sodium hydroxide that it was my acetic acid that was my limiting reactant? In that case, I'd be over here dividing by 0, which means I'd have an undefined, and that probably is a very good way to state what physically happens. We can't deal with that. The buffer system would break down. It would still change pH, and you'd want to be careful. So it is appropriate for you to be sure you use the right ratios and amounts of things in your buffer to handle what you think is going to be added that could change the pH. But this demonstrates the power of a buffer. Without the buffer, acetic acid changed by about 1 pH. With the buffer, the acetic acid changed by 0.1 pH. So that's a profound effect, because remember, 1 pH is a 10 times change. So we are definitely changing by a lot less with the buffer. And again, I want to reiterate, up here as we were doing the neutralization, we at the same time could have a dilution going on, because often our acid is a liquid and our base is a liquid. And so one of the methods that we do when even mixing a buffer to start with, much less when we neutralize, is we're mixing solutions. And when you mix solutions, you want to count for things in moles, and then at the very end be sure you're dividing by the total final volume to get your molarity. So that is not at all what I said. So back here, notice how I worked my neutralization in moles, and then at the very end divided by the total volume of solution to get molarity. And that's how we would account for that. Yes, you can account for it other places, other ways, and I respect that, but I have not found one that is as easy as this. If you just get in the habit of dealing with your mixing and your neutralization in moles and then dividing your total solution at the very, very end, you're less likely to mess it up. So I didn't want to warn you about that. Okay, so that's enough for the effects of buffer and how we could calculate a pH change with a buffer. We have several more examples coming up, but that'll be another video. So let's do some practice with buffers, and I'll see you next time.